All right, so we have a new friend. We can figure out the pressure from the, let's say we're underwater or even air or whatever. Most people like to replace this formula, and I kind of like personally to write it like this. I say rho GH, and the pressure is equal to rho GH. I like that because it kind of reminds me of like MGH, you know, potential energy. Just kind of looks nicer to me. So let's actually calculate something. Let's suppose we have a water tower, and the water tower is completely filled with water, and it has a height of 30 meters. And we drill a little hole in there in the tower, and voila, if there's a hole in the tower at that point in time, water starts to leak out. I'd like to know, what is the pressure of the water as it exits out of the bottom of that water tower? All right, so this is a relatively easy problem. So we know that pressure is equal to rho GH. The density of water is common knowledge, is going to be 1 times 10 to the third kilograms per cubic meter. That's the density of water. Notice that's 1,000 kilograms per cubic meter. So if I think you have a block of water 1 meter wide by 1 meter tall by 1 meter deep, it's going to weigh 1,000 kilograms. Water is really heavy. That's about 2,200 pounds. It's a ton of water. So to pick up a cube of water 1 meter by 1 meter by 1 meter, no one could ever pick it up. It weighs almost as much as a car does. Very, very heavy. Ships sink. You know, they get water in them. It's definitely true. G, of course, we're going to use 9.8 in New Jersey. And then we multiply it by the height. When we think of the height, what we really mean here is the depth. So it's the height of the column of water, but most of us think about it in terms of the depth of the water itself. So H is that depth. Now, if we're thinking about the water, it has a height of 30 meters high, and if we multiply that all out, we're going to end up with an answer of, I think I calculated this to be 2.9 times 10 to the fifth. 2.9 times 10 to the fifth, and our units are newtons per meter squared, or we can use PAs, pascals, and that's how we would calculate that. Now, an interesting effect occurs here. We know that the pressure depends upon the depth of the water. So when we had that water tower, and it kind of looked like that, we knew what the pressure was at the bottom of this water tower. Let's suppose, for example, now, I make this into, say, a cone shape. Something along the lines like that. What's the pressure at the bottom of this cone? Now, we know that this is 30 meters deep here. We know that it's 30 meters from the top of the cone to the bottom. So if we apply the formula, it doesn't say anything about the shape. How about if I have a straw? So I make a little straw, and the straw is 30 meters long. What's the pressure at the bottom of the straw? Well, if I use the formula here, pressure is equal to rho GH. The pressure here is equal to rho GH. The pressure here is equal to rho GH. Density of water is 1,000 kilograms per cubic meter, 9.8 times 30. Here, 1,000 kilograms per meter cubed times 9.8 times 30. Boom, same thing. Density is 1,000 kilograms per cubic meter times 9.8 times 30. Guess what? The shape doesn't make any difference. So the pressure is always going to be the same no matter what depth it is. All right, now here I am in the bottom of a swimming pool. So as I'm looking here, and I'm looking up here towards the surface like so, and you might have your little scuba mask on or whatever. So the question is, what's the pressure acting on me as I'm under the water? So if we look, the pressure comes from the column of water resting on my shoulders. So that pressure, we use this formula to calculate. All right, now what about the pressure coming at me from this side at this particular depth? Isn't there also pressure coming at me from that side on the opposite side at the same depth? And then isn't the pressure here balanced out by the pressure on the other side? And the pressure here is balanced out by the pressure there at that side. So as we look here, the pressure in the sideways direction kind of equals out. So when I'm getting squeezed on this side, I'm getting squeezed back on the other side, so this pressure kind of equals out. If it weren't true, wouldn't it be true if, let's say, the pressure was higher on one side of me, when I went underwater, it would push me this way? Or if the pressure was higher on this side of me, wouldn't it push me this way and actually make me move in that particular direction? Well, you know, when I'm standing there at the bottom of the pool, I'm not going left, I'm not going right. I'm actually going to stand still and stay in one spot. So I know the pressure laterally on either side is going to be the same.